Hello everyone. Today we are going to be going through how to solve some complex polynomials using our conjugate root theorem. Now our conjugate root theorem simply states that if we have a polynomial, for example a times z squared plus bz plus c, if this polynomial only has real coefficients, then two of its solutions will be complex conjugates. So at least two of its solutions will be complex conjugates. Now, if we have a polynomial, z to the power of 3 minus 3 times z squared plus 5z minus 3, and we go to solve this equation, we actually find that z minus 1 plus square root of 2i is a factor of this complex polynomial. If this is a factor, then we can use our null factor law to find a solution to this equation. So putting this into our null factor law, we would get z minus 1 plus square root of 2i equals 0. And if we rearrange for the solution, so if we rearrange for z, then we would get z equals 1 minus square root 2i. Now, using our conjugate root theorem, we automatically know that another solution to this equation would simply be 1 plus square root of 2i. So the other solution to this equation would be a conjugate of 1 minus square root of 2i. Now, this rule only works because our coefficients of this equation are all real. If, for example, an equation had an I out the front over here, we would not be able to apply this conjugate root theorem. So be very careful of that. Now, we already have solved our polynomial for two solutions. Now we have to solve for the third one. Now, from this, we can derive two of our factors, again, working backwards from our null factor law. So this one would give us z minus 1 plus square root of 2i that we already had before, so from over here. And the second one, again, working backwards with the null factor law, we would get z minus 1 minus square root of 2i as our factor. So to find the third linear factor of this equation, we first multiply these two factors together. So let's do that now. We get z minus 1 plus square root of 2i times z minus 1 minus square root of 2i. Expanding these two brackets out, we should get z squared minus z minus square root 2zi minus z plus 1 plus square root of 2i plus square root 2zi minus square root 2i and minus 2i squared. And we know that this I squared is equal to negative 1. So we can rewrite this term over here as minus 2 times negative 1, which is the same thing as plus 2. So we can rewrite that term over there as plus 2. So let's do that now. Plus 2. Okay. If we begin to simplify this by grouping terms, we can see that these two cancel out and these two cancel out. So if we begin to group these terms, or maybe we'll first write this a bit neater, we get z squared minus z plus 1 plus 2. Again, simplifying, grouping some terms, we get z squared minus 2z plus 3 as our expanded form of these two factors. Now we've found our quadratic term. We now need to find our other linear factor that we multiply by to get our expanded form of our polynomial. So if we were to rewrite our equation, we'd get z to the power of 3. So this is the expanded form that we were given at the beginning. This would equal our factorized form thus far, z squared minus 2z plus 3 times a factor over here. Again, to solve for this factor, which would be in the form z minus a, we can use our equating coefficients method to find our factor. So let's go through this together. If we were to expand these two brackets, we would get z to the power of 3 minus 2z squared plus 3z minus az squared plus 2az minus 3a. If we group our terms over here, we'd get z to the power of 3, and we can group our z squares. That would give us plus negative 2 minus a times z squared, and we can group our z terms over here. this would give us plus 3 plus 2az and minus 3a. So if we equate our coefficients, for example, negative 2 minus a, which is the coefficient to our z squared, we can equate it with the coefficient to our z squared found over here in our expanded form. So this would mean that negative 3 equals negative 2 minus a, which comes from here. Rearranging for a, we would get negative 3 plus 2 equals negative a. This would give us negative 1 equals negative a, so a would equal 1, meaning that our factor over here would be z minus 1. And this would also mean that our remaining solution would be z equals 1. So our three solutions, to summarize, our three solutions to this equation would be our complex conjugates of 1 plus square root of 2i and 1 minus square root of 2i, and z equals 1 would be our third solution, which we figured out using the expansion and equating coefficients method. As always, let me know if you have any questions. Otherwise, I will see you next time.